Good afternoon, everyone. So can you hear me? Okay, thank you. So last time we talked about this 2 degree of freedom example. So let me show you this slide, which is a summary for what we have done. Let me see. Okay, now, so look at this. This is our original system, right? We have a mass and the same mass M here, and with the 2 springs, K with the spring constant K and K. So this is a 2 degree of freedom system, and we can use the 2 coordinates, x1 and x2, to describe the system response completely. So that's the original system, and then we find out the nature frequencies and 2, which is omega 1 and omega 2. And as I mentioned, the lower one, because now we have 2, right? One is bigger than the other. So the lowest one, we need to put it as 1, so-called fundamental nature frequency. And then this is, you can see that the difference here is a plus and minus, because we are solving the eigenvalue, actually the eigenvalue of the system. So you know the eigenvalue and eigenvector from matrix algebra. So here, the nature frequency actually is coming from the square root of the eigenvalue. So we got 2. And then the modal vector, which is a corresponding eigenvector. But here it's related to the modes. So we call it modal vector. And it's basically showing given here. And as I mentioned, the physical meaning here regarding the motion will be like this. So like this, because this one we cannot find out the absolute value. So what we can get is only the relative displacement. So if we specify one, I mean, say A1, that means the corresponding amplitude for the M1, and we are able to find out the A2, which is the related, the motion of this and the other mass. So like this, right? If you move it to the right by 1, and then for this will be 1.618, it's an approximation of this value. So they move in the same direction, I mean, between these 2 masses. And then for at omega 2, and that will be, if you calculate, they'll be move it this to the right by 1, and then this, if you calculate, they'll be negative. So when we means in opposite direction, and with a 0.618. So we can see that these 2 masses, they move in opposite direction, right? So I hopefully can see my hand. So now, because if you look at these 2 hands, it means 2 masses, right? So that means M1 will be, both will be moved, I mean, in the same direction. And then for omega 2, I mean, there will be maybe, let me see, let me close the virtual. Let's see. Let me just close it. Okay, now you can look at this, right? So we have 2 mode. The first mode is they will move. I mean, they'll move in phase. I mean, like this, in the same direction. And then the omega 2, they'll be, say, in opposite direction, right? 1, 1, 2 move like this direction, and the other will be like this. I mean, if they move, will be like this. Okay, something like this. So then you can see the both masses, because now before we only talk about single degree of freedom, we only have 1 mass. Now we have 2 masses. There are different interaction between them. So that's why here it's very important not to mix these 2 modes, because for these 2 modes, you can see that they have a corresponding motion movement. So you can expect, if you have more degree of freedom, and they are going to have more interaction. So this is a 2 degree of freedom system. We have 2 nature frequency. We have 2 different modes, and the motion in this case will be like this. I just explained, right? And then for related to this motion, sometimes for simplicity, we only need to say point out the key, say the key difference. Okay, the key difference and between them. So we can have a simple sketch. And I'm going to put it down here at the bottom. So for simple sketch, let me show you here. So instead of, instead of seeing the ceiling, I mean, I'm going to, you can see our beautiful virtual campus. Okay, now let me sketch the diagram will be like this. So it's related to the I mean the model vector here, right? So we can simply call, and that will be so-called mode shape. I'm going to put down. Mode shape, okay? It's related to the mode. You can see that the mode is which is a model vector here. So the first one I'm talking about is omega 1. So we can just draw some key feature. For example, this is a fix, right? I mean, then for this is a reference, it's like 0. And for M1, I mean, this is a point I just put down. I want to mention it's just a point. I mean, then and it's a point, right? Basically, your above means positive, and below the dash line means will be negative. So it's a 1, so you'll be say from this point, I mean from the reference, you'll be 1 here. And then for the M2, you'll be 1.618, right? So then we can draw another one will be 1, and 1.618 will be larger like this. And so you have 2 points. Let me just point out, this is a 1 point, and this is a 1.618 will be 2 points. So let me make it, sorry, it's not a line, it's just it's a point, okay? And this is another point. So this 2 point, I put down, I try to use a circle. And this is another point. So I just connect it. I mean, this is a 1. So the value here is 1, and this point is a 1.618. So we just connect this point with, this is originally 0, so this is a straight line here. And then I connected another straight line, right? And I call this as a first mode. First, I mean the ST and mode. And then for second mode, which is showing here, you can, they'll be like this. I can sketch it again. This is a fix. And then it's a reference here. This is a 0 reference line. And then we have a 1, is still 1. I mean, for this point, I mean, for M1, this is a 1. However, in this case, for the M2, it will be negative, so it'll be below this line, and here will be minus, negative, and minus 0.618. Okay, it's negative. And then if you connect it, it'll be straight line, and connect these 2 points, another straight line here. Okay, this is a straight line. And so this is the second mode. We can just call this, I mean, 2ND mode, second. So this is ND here, okay? So now you can see, look at this at the bottom, right? The sketch is a much simpler than you don't have to draw the original one like this, right? And this will be simple way for you to draw. I mean, and this one also will be good for you to look at. When they both mesh are in the, I mean, say the top side, and like this one, the second mode is the one on the top, and the other will be at the bottom, right? They have a different in different direction. You can see will be plus and minus, so you can see the change clearly, right? And this is both in the same direction. Will be both are either positive or both are either negative. I mean, both are negative, then we call this as the first mode, and this will be the second mode. Okay, so with this, we can see we can draw the mode shape. I mean, for this 2-degree of freedom system. So at least now you will be able to see that the 2-degree of freedom system, and compared to the single degree of freedom system, there are some differences. So any question about this? Okay, so it's fine. So if this is okay, now let me show you the homework problem again. Here, homework problem assignment. Okay, and I mentioned last time, right? So in fact, this suppose already has been uploaded to the website. You should be able to see that in the course website. So this is the second assignment. The due date will be October 26th. So, well, will be Monday after next week. So you do have time to work on that. So for this assignment, you also look at, I mean, there are 2 pages. Let me show you the second page. And 3 problem I'm going to show you will be the last problem. Problem number 3 here, right? So this problem is similar to the example I have just mentioned, right? So you can see we have 2 maps. So but now it's in vertical direction. So this is M, and then the other mass here is also M. And the connection, you can see the connection, right? Here's a K, the spring, and here's another K, I mean another spring with the same stiffness. And it will be, the ground here is fixed. And I want you to, for this spring mass system, and you will be constrained here also specify, you can only move in the vertical direction, in the vertical direction only. So you need to derive equation of motion. So this is the first thing. And second is you have to find out the nature frequencies. Okay, right? So this is you expect this is a 2 degree of freedom system. We have 2 masses. Here's one, here's the other one. So you need to coordinate to describe this system. And then after that, you have to find and also sketch the mode shape. The mode shape. I just show you, right, how to draw the mode shape. So there will be, this is some practice, I mean, I want you to do. So the good way for you to do is you can go back to check the notes. I mean, we have gone through, and then redo it, and then you'll be able to work on the new problem. So they are quite similar. So this is one of the homework problem. And so problem number 3. And for back to the problem number 2, and this problem is accelerometer we have discussed earlier, right? And this is like design problem. And so you need to use, I say, the relation, the expression we find out, right, between the so-called major acceleration and true acceleration, and to work on this problem. So if you know how to do it, actually, this one also is not that complicated. You can get it done also, I mean, without spending too much time on that. So this is a second problem. And back to the first problem, I mean, this one. So maybe just look at the problem first, okay? So this is a simplify the suspension system. So I want to explain here will be in this case, you can see it's just like a vehicle. And this vehicle, we have two, say, actual, I mean, basically front and rear. I mean, this is so you can treat this as what, like motorcycle or even like bicycle, right? But even the rear vehicle, you can see here, I put down 1,000 kilograms, so it means kind of heavy. So it's like can be a regular passenger car. But the front wheel, I mean, two, we combine into one, and the rear wheel, I mean, both can be combined into this one. So basically, you can simplify just a two. So we have a two wheel here. And then the car body end, okay, it can be given like this. So now the vehicle is moving to the right, I mean, with a velocity, I mean, v. And so with the MCK, you can see mass, dash part, and spring system. And so it is a single degree of freedom system here, because we only need to specify this m, right, the coordinate for this m. However, the row condition will have a basic excitation. So we do consider basic excitation, right? So you need to consider this, and you'll move to like this. And now is if for this suspension system, this car will have a row conditions like this. It's a step. I just assume this is a step. So hit a step, and with you can see the dimension are given here, right? The height is not a big one. If a big one, you'll be a crash, right? So you can see it's just about like 7.5 centimeters. So it's it's okay. I mean, right? I mean, for hitting this kind of situation. So, and the length is also given between the front and rear wheel. I mean, this is a L is given, and also MCK are given here. Okay. So here is another assumption: is the vehicle travel to the right, and you have a wheel basically will be in contact and with the road all the time. So this is a, I mean, we assume so. And also you have to consider when you hit it, the front one will hit it first. This is a step. And then after some time, so this is related to the L and also the velocity, right? And the rear wheel also will hit the same step, right? So this is a simplified suspension system, but it's also, it'll be good for you to consider this problem. In fact, this will be a good approximation and to simulate the real situation and with basically the concept we discussed so far. So how to do it? I mean, here is the question, right? The first one, again, you need to derive the equation of motion. And for this so-called base driven system, so it's a base excitation, you have to derive equation of motion. And then after that, right, based on the equation of motion, you need to find the expression, I mean, for the response. So analytically, you can do that. Remember, we also discussed impulse response. We said the convolution integral. And we know the excitation function, right? I mean, this is a step function, is one. And then you are able to, I want you to find out the expression for the motion, the vertical motion of the vehicle, and following basically the roll height this change here. Okay, so this is a closed form expression you find out first, and after that you can, since you already got the expression, so you can do simulation with the use of say MATLAB. It'll be easy for you to do simulation. So if you want to do simulation, you need to specify the velocity. The velocity is 24 meter per second, and with the simulation you also can plot the motion and with respect to time and discuss your findings. So with some simulation. And number three is since you already have a simulation, the program, the code, right? So you can use a computer to help and for you to explore it even more with a result in B, and you will be able to do more simulation to check. So what will be the maximum height and attainable by the vehicle, I mean, at any speed, right? That means you change the speed and to see what will be the height, the corresponding height. Then you are able to find out what will be the maximum height. And if you find it, what will be the corresponding speed? You can, basically this can be achieved, right? And then with what speed of the vehicle, then we'll have the residual suspension motion. So that's basically, and this one can be minimized. So I want, basically this one is to utilize B here and do more simulation, and with the finding, you should be able to get it. So I expect you need to spend more time on this problem number one, as compared to problem number 2 and 3. So that's why you can see the points, right? Problem number 1 is 50 out of 100 points. And then for the problem number 2 and 3, and each basically carry 25 points. So that's about this assignment. And so, do you have any question now you want to ask? Okay, no question? So if this is fine, and let's move on. So before we are going to talk about, say, structures control, and now let me basically try to describe the project. I mean, a little bit more. I mean, because in this course, to have a course project. So let me open project. Okay, yeah. So let me talk about project. So this project here will be the course project. And so you can see that there'll be a kind of review and proposal given the time you have. So I'm going to talk about the key, the content you may have in this, say, the course project. So the topic, in terms of topic, first of all, you'll be individual project. So each of you will have a work on your own. And then second will be, the topic you choose will be related to this course, I mean the smart materials. So you'll be one particular application and using one kind of smart material, they'll be fine. And you can emphasize on application or some particular issue, and they'll be also okay. I mean, so does that mean to be exactly application? I mean, as long as it's related to this course, smart material and structures, and they'll be okay. So it is very flexible, and so all of you can think about it. What are you going to do? I mean, in this course project, and basically the content will be, the first will be introduction, right? So, and this will be, say, for example, the significance of the work. So let me see. And so why you pick out this, I mean, this topic and what has been done. So you need to do some literature, I mean, the literature review. So nowadays, internet is very powerful, right? So you can use some keywords and to search for related, I mean, the research or papers, and have been done, have been published already, or even some internet website, they are also fine. So that'll be the first part, and then you want to consider significance, right? And this is a reason you pick up this topic. But usually you want to know the significance. That means you should know the problem and the issues, right? And which part, I mean, do have what kind of potential problem, and the author or other people may not tell you exactly. So you have to say, read it and understand, and basically to find out the problem and issue. That means this will be the opportunity for you to consider. So, and this will be part of the motivation, right? You pick up the particular topic, I mean the issue, right? And I already mentioned this is a one you have, and literature review should be part of it. And for literature review, it usually is not just to pick out a single article. It's not just one paper, okay? And you have to consider all related work. So if you have many, and you try to be more organized, I mean, to consider, so you maybe categorize it, I mean, into different aspects. I mean, if it's too many, to be more organized, you'll be helpful, and for you to consider, I mean, what the contribution done by basically previously by others. So I mentioned, you can see, do some categorization, right? I mean, to have to organize and you also need to know the state of arts. It's just, don't just look at like 10 years ago or even 20 years ago, right? And especially some work has been done more recently. I mean, that'll be also good for you to pay attention. And I'm not saying, say, you don't have to look at like papers in 20 years ago, because some idea you saw it and could be done long time ago. So that's you have to basically have provide basically done more kind of comprehensive literature review, and with a state of arts, and do some categorizing into the different aspect, okay? And so with your own discussion, because other people, this is what you have done, and you don't want to don't just pick up a review article, say, hey, people already, they have done everything for you, okay? So this is not a intention, right? I want you to go through that and to have this kind of, say, training or practice. And of course, for some topic you pick up, if they have a review article, you can also take it as a reference, as one of the reference, they'll be fine. So all the literature you review, you need to put it into your references, I mean, to acknowledge it. And those has been done. And so you have to do that, because this is also related to academic honesty, right? And if there's some figures you directly use, then you have to put down in the figure, you have to put down the specific reference number for that one. It's from what source? It's from a paper or from the internet. Then basically you need to put it down, I mean, especially into your report. So that's about the discussion about still many also related to other people, they have done their work. And then after that, after the discussion, you need to put down the problem statement. I mean, what will be the key problem, and you would like to address, right? So here, what is missing? So missing means this will be your opportunity. And as I mentioned, a lot of issue and problem people, they are not going to, the author are not going to tell you exactly. And maybe some paper, there are some discussion about the future work, and this could be something they imply or they provide. But a lot of, say the situation is you will not get it directly. So you have to think about it and to find it out and what is missing. So, and why it is important, right? The problem is important. You want to work on that. And so with that, after this part, and then I want you to consider the proposed, the task. And with the task, that means you have to also consider what would be the possible method, the methodology, right? So this is a part. And now this is you still have time to work on that. Maybe you have chance to get some preliminary results. So either say experimentally or say with some simulation. Okay, some simulation. If you have, it'll be good for you to include this part. I mean, the preliminary results. So this is the procedure here will be related to the method, right? Especially for some experiment, if you are going to do, what will be the procedure, and you would like to use, and so if you have more result, it'll be easier for you to discuss in the next part about the impact and contribution, right? And if you do not have much, so maybe what you can do is this is something you expect, because if you actually make it, then you based on the result, then you can just say it, right? You can just put down some statement. But if you don't have it, so that will be expected impact and contribution. So, and also what will be the time you need in order to work on those proposed tests, right? One by one. So, and the summary about everything basically you have done or you like to consider. And as I mentioned, the references, and this is quite is very important. You need to include this part. Okay, so this is about the general the content. I mean, a guideline about the course project. Any question? Okay, no question at this stage. So when you have time, you also can think about it and do it earlier, and then you have more time to basically to work on this project. So the presentation actually is already course scheduled, right? So it'll be December 2nd. We are going to spend almost a whole afternoon. I mean, the 3-hour, 3-period lecture. I mean, for basically it's the last week before the final. I mean, for you to give the presentation. So you know that the time could be limited. I mean, for each of you, you're doing the individual presentation, but it's still good for you to share. I mean, the best you have done for this course project, right? It's like maybe each of you could be around 5 minutes or even 4 minutes, and then you can do that. Just use a few slides and to do that, okay? To highlight the key findings and also the idea you would like to work on. So that's about the oral presentation. And the written report, you also need to complete the written report. You'll be due on December 11th. So suppose this will be after the final exam about that. So that means this will be the last day. You finish all the coursework, including both the exam and also the project report, and presentation will be done earlier. I mean, okay. So there'll be the schedule about this. So let me see. And for this, I will ask the tutors to upload. Let me see. To upload the report guideline. Let me see. I should have. Where is it? Oh, here. Okay. Now you can see that. So the Word file you can use it as a template for your written report. So and the Word template will be uploaded to the website. So later on you can download it. Okay, so don't worry about that, the file. So now this will be your title. So you need to replace it with your course. I mean your project title and your own name, right? And your own name and also your student ID and email. So you just replace it with your own. And you can see the report in general, including abstract, and then the keyword you need to put down. And here, this is a general information. It'll be good for you to read through it. I mean, because this one itself is a template, but at the same time, it's also provides some the information related to the project and also the report, right? And like a format issued, and you use the same format, and then title, subtitle, heading, subheading, right? And if you have a equation, and you just put down the equation, I mean with the equation number, and then for the illustration like figures or diagram, right? You can put it down and with a caption and references, right? Those are key elements you should have. And the submission, the date, I already specified regarding the submission date. And then the references, it could be, I mean, some journal paper or even some reference book or website. So you need to just put it down, okay, like this. And for the content, I mean the length, in this format, I expect you to, for the report will be 4 to 6 pages with this kind of format and the font size. So you don't have to write, I mean, too many, I mean, there's no need, and just, I mean, too simple is also not good. So you'll be a good range between 4 to 6, I mean, pages with this format. So that's what I want you to basically to prepare and for the report, written report part. So any question about this? So any question about this? Okay. So if this is a fine, then it's still early. I mean, now it's you have almost, I mean, 2 months to work on that. I mean, right? I mean, if you consider the due date for submitting your final report, so you can do it earlier, and then later you'll feel more comfortable, right? Regarding the coursework and maybe also others, including your research. Okay, so that's about the project. And again, for this template will be uploaded to the website. So no problem. So if no, then now let's go back to the note. So now it will be the new note. I mean, I put it as a number 3, and suppose also has been uploaded to the website. Now, we would like to consider, I mean, we would like to discuss so-called structure control. And because of smart material structure, why we put down the structure as part of it is one reason is we want to control the structure and to make it better. So better here means with better performance or higher performance. So I'm going to talk about the method, to control structure. And we can categorize it into four different structural control. So I'm going to talk about it one by one, for structural control. So the first is a passive control. So in terms of name will be passive, active, and active-passive hybrid, and semi-active. And what are they? And I will basically highlight the key features, and I also would like to give you some examples. And then with that, it should be okay for you to know about the structure control. So the first one, passive. So the passive control is the simplest one. And so for this, in general, you'll be what? If you are talking about the MCK, remember we have a single degree of freedom and later on like multiple degree of freedom system. And then we can basically, we can derive the equation of motion. And I show you already. So if we can use the matrix, let me just put down matrix. Okay, nx double dot plus cx dot and plus kx equal to f, right? So this is a one. We can have. Generally, if we have a multiple degree of freedom system now MCK, and they become what? They become matrix instead of scalar. Okay, if this is a single degree of freedom, MCK will be scalar. So this is a matrix. And the so-called passive is those parameters, for example, those MCK, mass, damping, stimulus, they are parameters. So they can be synthesized offline. That means they can be designed, they can be determined offline, right? Before we are actually make it or implement the system. So this is a parameter here, means MCK. But we don't have to really, some could be MCK, you would like to consider them together, but some could be more crucial than the others. It depends on the system, the actual system, and we basically have. So later I'm going to give you some example. So here will be, the system will be stable, for this system, and no power will be required. And the stable will be related to the damping, as long as the system do have the damping. And remember when we consider under damped system, right? And with damping, the response will be getting smaller and smaller. You'll be stable. You will not die out. You will die out. You will not diverge. So you'll be stable and no power is required because we don't need to apply any additional or external power. And later you can compare this one with the active control. So this is a good feature. However, the design will be fixed and no feedback will be used, so therefore the performance may not be good enough. So if you want to really pursue really high performance, and now passive control, and may not be really say very, very good, okay? So I would say that from design point of view, if the passive control, since this is a simple, already can meet the requirement, and then passive controls, passive is still a good way to do. Okay, so, but if not, and this is also related to why many people working in control, the control in our department, we do have many control courses as well, right? So here the control will be related to the next one, the so-called active control. So control part actually is to deal with this throwback, the last one, right? We try to have a feedback control, feedback action. And with the feedback action, the performance can be much higher. We can obtain the high performance. And how to do it? And how to do it, that will be another issue, okay, right? So maybe let me mention the feature of active control, and then we can just go back to, I'll go back to show you, illustrate some examples, a couple of examples for each of them. So that's my plan to do. So now this is the same, the slide. I can see the second control is so-called active. You can see the passive has been changed to active. And for active control, we are going to use some sort of actuators, right? We call it force actuator. And that means the actuator will be able to provide like force or torque, and for us to control structure. Structure is the target. So, and you can see that compared to passive no feedback, right? And now we have a feedback has been used with a closed loop feedback and high performance and can be achieved, right? That will be the purpose. And then there's no free lunge. So for the control, as compared to the passive, you don't need any power, right? But now for the active, basically in order to obtain the high performance, and then we need to apply, to need some power, and usually the power requirement will be high. Usually will be high, okay? And also since it's a control, when you study control course, stability, right, is very important. So because why is it important? Because with control, potentially it can be unstable. And that could be even worse, right? Worse than before. So the purpose here, the control is you want to obtain better and high performance. But if the system is unstable, then we'll be in trouble. So that's why you need to consider the stability, right? So that's why for control, you have two aspects. It's important. One is a stability, and the other is a performance, right? And now for this in particular, for this so-called structural control, is a part of the application scenario. To use control, right? It's one of them. Use it. So you also need to deal with that. But the good thing here is the difference here will be the control you study will be more related to control, the theory. And here we only, when we need it, we only use control as a control application. And for basically structural control will be one of the control application. So that will be the difference. And of course, if you want to know more about control, you can, then when you study control courses, it could be more than one, and you can spend time and effort on that. Or if needed in your research, you also can look at, the literature to find out, basically to find more about it. So there are quite a lot of sources and resources you can do. So that's about for this slide, about this one. So I'm going to give you examples about that. Before the example, maybe now it could be good time for us to have a 10 minutes break, and we'll continue. After 10 minutes break, then we can finish like 5 minutes earlier. Okay, so let's have 10 minutes break now. Okay, so now let's continue. So back to that one, I mean, let's mention the structure. Let's talk about general structure system. So let me see. This should be general GNI structure system. So in general structure system, we can categorize into two. So this will be structural. Okay. So we already know basically it will be model like this: mx double dot plus cx dot and plus kx, and it will be equal to f, right? So it's dynamic system. So it will be those x and f will be function of time, right? And so this one we call this is the so-called, if we can model like this, it's called lumped parameter system. LUMPED, lumped parameter system. The system we are talking about. So that means this will be like MCK. I mean, they do not, those parameters, they do not depend on the spatial variable. So why there's another something different? Let me say it's called distribution. Wow. Move. Okay, so this is the news, I mean the one. So the other will be, so for comparison, the other is distributed system. Distributed and parameter system. So distributed parameter system, or sometimes we can call this as continuous. Continuous parameter system, continuous system. You can simply just call continuous system. So what is that? Is for example, we are going to have a structure like this, right? I mean, like a beam, and then and then may not be uniform. I mean the cross section. So you can see that in this case, for this kind of structure, the stiffness and mass is also a function of the location, right? Location. So we call it spatial coordinate. That means not just the time, we also need to consider the location. So in this case, because of that, and you'll be a PDE, the partial differential equation. I mean PDE. Okay, this is better. I mean you can recognize PDE, right? And so the data you will see that we are talking about that. I mean like for beam structure, and because this is a quite common, and it could be small and could be quite big. For example, like bridge structure is also, we can basically model it as a beam structure, right? So this will be distributed parameter or so-called continuous system. And so suppose for this kind of system, you obtain PDE. The good thing is for this ODE we have for the lumped parameter system is even you have a PDE, right? But through the discretization, the PDE, through discretization, let me put it down, PDE, it can be changed to ODE. So partial differential equation can be changed to ordinary differential equation. And this process is called discretization. TION, I mean TION. Discretization, I mean the PDE, that will be changed to the ODE. So there'll be kind of the reduced order model. It's kind of approximation, and for us to find out a solution. It's quite common for us to do that. So that's about the general structure system we can discuss. And with this one, now we can go back to the passive control, right? So the passive control, as I mentioned, the parameter we are talking about the MCK, and then most of the time, I mean, we may deal with C, the damping, because it'll be effective and to basically change the performance related to the performance. So for the passive control, I give you a couple of examples for passive control. So passive control we are talking about. And example, so I have two. So suddenly I just hit the change color. It's okay. So now let me move out a little bit. So let me just use a non-parameter system first. I mean, say 2 degrees of freedom. I'll say it's one first, maybe just 1 degree of freedom. It's a simple one. MCK. So that's what we considered before, right? I mean, this is a 1, M, K, and this is a C. So it's quite common, right? As I mentioned, we can design or choose MCK, and in order to meet the system requirement, especially the damping C, because damping, as we discussed before, right? For a single degree of freedom system, the damping is an undamped system. Under damping ratio between 0 and 1 equal to 1 greater than 1, and the response will be quite different. So it's quite very effective to change the damping coefficient C and in order to control the structure. So this is an illustration. And if want, sometimes it's not good enough, we can just add 1 more degree of freedom. So I just move up a little bit. So that means based on the original one, let me just sketch it again. So this is the original we have. Right, original. So if you want to control the movement of this mass, so there's one method is on top of it, we add additional degree of freedom. Okay, additional one, let me change color. So this is a spring, and there's another additional dash part. And so this is additional, let me call it M sub A, I mean subscript A here, and this is a K sub A, and this is a C sub A. Or you can treat the subscript A as an additional or auxiliary. I mean the additional, the coordinate. So you can see this is an additional one. And the purpose for you to do that is, now this is you have an extra, say the parameters, M sub A, C sub A, and K sub A. And the purpose is when this is moving, some sort of energy will be, say, transferred from the original structure, the whole structure, and transfer to this is substructure, right? And not just a transfer structure, and also some of them could be dissipated like through the dash part, right? So in that case, this can be minimized. So this method, in fact, if you study vibration, this is a very well known, it's called vibration absorber. Vibration absorber. Okay, vibration absorber. So if you check the keyword, you can find it. It's the textbook even have some section to talk about that. Because this is a 2 degree of freedom system. If you want, you also can derive equation of motion and to find out related to the amplitude issue and even do optimization, right? So already this is in literature, you can find it, or even in textbook, you can find this one. So this is also the passive approach, but the degree of freedom is different. Earlier, this is an illustration purpose. It's only single degree of freedom, right? And now this is a vibration absorber. It's a 2 degree of freedom system, 2 degree of freedom system. And for us to minimize the movement of the original, the mass, M, right? So this is an example for so-called passive control. But now I'm also giving you, the, for the continuous structure, right? As I already just mentioned, right? For example, it's a beam. So this kind of structure is a very, say, a slender structure. It's long, but it's a kind of thin, and we call this as a bin structure, right? So for this kind of, this is structure if you want to control. I mean, for this is a structure we like to control. And which is also quite common in many structure systems. It can be micro level, I mean very small. Okay. It can be as large as like the bridge, right? This is a like large structure. So the scale is not is okay. We can deal with that, either small or large. So, and one method for us to consider is for this kind of structure. What we can do is also quite well known. Let me specify. You'll be just add a layer, and this layer is a material, is so-called viscoelastic material. I mean for this one. Okay, viscoelastic material. So this material is kind of like a rubber, for example. It's kind of soft, and you put it onto the structure, you can try to reduce the vibration of the structure. And so it's one, but to make it even more effective, and usually people consider one on top of it and add one more layer. I mean on top of it. This is another layer, sorry, just on top of it, right? Just on top of the viscoelastic layer. So this layer, the top layer, we call it constraint layer. It will be a layer, L-A-Y-E, constraining, C-O-N-S-T-R-A-I-N-I-N-G. So, and this layer, the top layer, you'll be usually kind of stiff, especially compared to viscoelastic. So viscoelastic now become the middle layer, right? It's a middle layer sandwich between the constraint layer and the original, the whole structure. So that's is a very also quite say the popular way and as a passive control method and to deal with the structural control. And this one is also quite well known. Let me give you the name for this. It's called constraint layer damping treatment. Constraint layer damping treatment. Okay. Constraint, that means you can see that the viscoelastic layer has been constrained right in the middle, right? And so this is beside the vibration absorber, and this is in fact, you also can find earlier paper, I mean, maybe the last century, 1970 something, and there are some paper that they talk about that. And it's already quite mature about this. And so this is a passive method, so we may add passive in the very beginning. It's called passive constraint layer damping treatment, passive. Okay, so I give you a couple of examples, actually 3, but one is under the lump parameter system. And on the right, this is a continuous structure, so-called distributed parameter system. But so far, this is still passive control. Okay, now next, let me show you the active control. I mean, that will be good for you to compare and to compare the difference, right? So the active control, the example. So I try to move it a little bit, and then move it down a little bit. Then for active control, I just put it here, active control, active. And then example. So the still I want to show you will be the example. So the example, the one will be, so let me put it here. So it's a mesh, and then we have a spring, and then the damping has been, the C has been removed, and instead, and we put a F. So this is a fix. So on the right, this is F here means we do use like shaker or like actuator, shaker, even including shaker motor, right? If to provide force. So with the force, then you can control the movement of the M. So this is I use F here, means that this is an active control. So implementation, it could be, may not be exactly like that, okay? I mean, this could be some sort of device can provide force. But this is a non-parameter system, and you can see the difference. I change, basically original one is C, right? And now I change to F, the force, can provide the force. And now for the bin, the same bin example, the structure, this is also still active control. For the same, say the bin structure, we are talking about the structure we want to control. And now you can put a patch of the element, and this one is we can use one of the smart material. In fact, we discussed before, it's a piezoelectric layer. It's a piezoelectric layer. And then in order to do it, we can apply the voltage, right, to this piezoelectric. This is a V, to this, the top, and also the bottom of the piezoelectric layer. And this will be grounded. That means we can change the voltage, I mean the AC voltage to control it, the movement. So how is the basic principle? Now let me have some space. I would like to illustrate. So for example, the bin is a cantilever bin. Cantilever means the boundary condition, one end is fixed and the other is free. This is like bin. I just draw very simple one like this. 9 means it's a bin. So the left hand side is fixed and right hand side is free. We call it cantilever bin. And now if a piezoelectric layer, it will be put it like here. Okay, let me make it longer. So like this here, right? And then when the bin is vibrating, say the upward, so let me just, you'll be like this, right? Bin will move like this upward. In this case, for this piezoelectric element, we can apply the voltage, right, to what? In this case, and try to extend it, right? So extend means make it longer, right? So you will extend to these two directions, left and right. So in that case, you will provide bending moment at the boundaries of piezoelectric layer, bending moment. So you try to rotate it, push it back. So we can push this bin back to the reference, I mean to this like horizontal configuration, right? So let me draw another scenario. Will be when the bin is moving downward. So this is a bin. So now bin is moving downward, okay? And so in this case, we still have a patch of, say, the piezoelectric element here. So in this case, we want to change the direction. The movement will be, we try to shorten the this piezoelectric layer on the top. You can see the direction here, right? I mean, before this is a extend. Let me draw it. It's extension. It's like this, right? And now this is in opposite direction. Shorten it. So if you shorten it, you can see at the boundaries of the bin. So you will have create this like bending moment in this direction and in this direction. So with this, you can pull it back. For the bin is vibrating downward, you can pull it back to the, I mean the reference, I mean the horizontal configuration. So you can see that when the bin is moving up and down, and you just keep changing the voltage applied to the piezoelectric layer, and we'll be able to reduce the vibration or reduce the structural movement. Got it? So this is you can see the say qualitatively what's happening about this bin, and quantitatively later on we will derive the equation of motion and also find out the solution to do that. Especially for the bin example, we'll do that, okay, with the use of piezoelectric material, and you will see later on for the more comprehensive study about that. But so far, for the concept, and this is what I want to mention about this concept. So this is fine here. And let's go back to the PowerPoint and with more discussion for this. So we are talking about this, right? So the parameters I mentioned for the passive, and this will be the parameter here will be MCK. I mean, that means MCK we are talking about, right? And the stable is really mainly due to the C, the damping, right? So now I have some slide about the active control. Just follow the discussion we had. We will come back for the discussion for this. And like this one. So this slide is to show the active vibration control, right? And now it's not just effective for the bin. We also can consider the structure, right? And so the structure, it doesn't need to be the bin structure. It could be also more general structure. So I just draw some more like upstream the shape, as you can see. So, but this one is to show you. You can see this is a piezoelectric actuator attached to the structure, and we have a sensor, and right to measure and to get the response. I mean the structure response, and then with that the controller will decide how to apply to the voltage applied to the piezoelectric actuator. So here you can see the closed loop feedback has been formed, and with that, now you can see we just highlight this part, right? For the piezoelectric element, if you try to extend it, for example, when the bin is, I mentioned the bin is vibrating upward, and we do have this kind of scenario, right? And so the applied voltage will induce a stress, and the stress, because it's bounded, I mean for the piezoelectric element bounded to the structure, you will create a bending moment at boundaries, at this, I mean both ends, and therefore we'll be able to, and the moment will be able to utilize and to control the structure. Okay, so this is the concept. And as I mentioned, and later on, I will show you mathematically, we are able to derive the model. And you can also verify this concept I mentioned here, why you have a bending moment at boundaries. So later on, you will see that, okay? But you'll be, I mean, a few weeks later when we talk about this, the structure, the modeling, and control issue. But now this is what I want to mention about, basically about this. I mean, about the active control. So example I show you already. So now let's go back to talk about two other control methods. Right? We have discussed two, which is the first slide is a passive and active. Right? So now if you look at these two methods, and both methods have their own pro and con. Right? So for example, the good feature for the passive is a stable and no power is required, right? And but the limitation is a fixed design and no feedback, so performance may not be good enough. And active, the good feature will be high performance with a feedback, right? But the problem issue will be the power requirement and also the stability issue. So can we find a way and try to combine these two methods, active and passive? And that means we try to keep the good feature. And then on the other hand, at the same time, try to get rid of those negative effects if we can. Or if you cannot get rid of it, at least you want to find a way to reduce the negative effect, right? So that is a purpose. So let me show you, there are two ways to do that, and we'll be showing in the next slide and followed by examples. Again, I'm going to show you the example. So the one will be now, the next one will be active-passive hybrid. We call it active-passive hybrid control. So what are they? And this will be, the purpose here is we try to integrate the active system with a well-designed passive element. So you can see here, there are some keywords, right? One key, basically key will be active and passive. Yeah, this is right. But of course, we don't just do it upstream. It should be well-designed. If you just put it together, it may not be beneficial. I mean, it may not be bad, get a better one. So that means a simple mass I can use here will be like this. If you treat the active and passive as one, like active is one, passive is one, I mean number, and you put these two together, active, passive. So 1 plus 1 is what? 2, right? So, but if you get 1 plus 1 equal to 2, well, it's pretty straightforward, no surprise. But if you can have a, put these two together can be greater than 2, for example, 3, that means it's good, right? It's good to put these two together, right? So that'll be the target and idea. And so there's another method will be like semi-active. So that we'll talk about it. But both of them you can see. I mean, here for these two methods. So semi-active we'll talk about it a little bit more later. The purpose is to combine the advantages of both, from active and passive. So the active, the advantage is, as I mentioned, is a feedback, right? And with high performance. And the passive system is the system will be stable and it's so-called fail-safe. So fail-safe means if the active part fail and the system still safe, right? In terms of stability or even the performance still not that bad, okay? So this is the target. So now let me show you the active-passive hybrid controller example. And after that, we'll come back to talk about the semi-active. So for this, I think it's better to use the board here. I mean, I can sketch, do something here. Now, the method. So here the method will be, this will be, I just put it down, active and passive hybrid, okay? It's a hybrid. So the example, let me, first one still non-parameter system, still use a single degree of freedom example. It's still N. And then this will be K, sorry. And then the middle one, so this will be K. The middle one will be, let me put it F. So this is the active part. And then this will be the dash part. Right. So for the single degree of freedom system, you may feel, hey, actually the C and K, this is from the passive, and the F here is from the active, right? So we have an active passive hybrid in this case. So that's about the single degree of freedom system. And so illustration purpose. Now let me show you another, again for the bin. For the bin example. And this will be the structure we would like to control. Structure we want to control. Now, maybe it's good to look at the previous example here. I found the top here, right? So this is a one we have. Earlier example, even for the passive, yeah. This one, the so-called constraint layer damping treatment. So what we want to do is, earlier we have this viscoelastic layer, right, sandwiched between the top layer and the structure. So now, one way we can replace the top layer, the constraint layer, with a piezoelectric layer. The piezoelectric layer, this one replace with piezoelectric layer. So that's what we can do. That means combine this approach and with this one, the active. We can see originally here we have a piezoelectric layer, right? So we replace the top layer and with this one and create a so-called active-passive hybrid. So I'm going to redraw it, showing here. Just redraw, it will be like this, as I just mentioned. So we have a two layer, right? So the middle layer, this is a viscoelastic layer. Viscoelastic, I mean the viscoelastic layer. And then the top layer now is a piezoelectric layer. right? Piezoelectric layer. So piezoelectric layer, you want to control it, so therefore you apply voltage. Sorry, this is just a straight line. And then here, right? I mean the top and bottom of the piezoelectric layer, you need to apply voltage. So it's very similar to the constraint layer, but the top layer has been replaced with a piezoelectric layer. So we call this as an active constraint layer. It's not a passive. It's called. So okay, active constraint layer, which can just call it ACL. I mean from the initial ACL and damping treatment. So that's ACL, the damping treatment. And this is one of the basically configuration has been studied back to 20-something years ago, I mean, about the ACL. So what will be the principle about the operation principle? I can show you, use a slide and do the more discussion on this. So use this one, 2 slides, couple of slides. First one, look at this. So this is you can see the title, active constraint layer damping treatment, right? So it is an active passive hybrid approach. So the ACL is coming from the initial ACL, I mean the ACL damping treatment. And now let's go back to the structure on the left. You can see for the structure, we have a viscoelastic layer sandwiched between the top layer, now is piezoelectric layer, right? And then again, with the sensor together to measure the response of the structure. And then to the controller will decide what kind of voltage will be applied to this piezoelectric layer, right? Well, again, the closed loop feedback will be formed, and then we are try to control the structure, I mean the movement of structure. And on the right, let's take the cantilever beam as an example. So the cantilever beam means the left-hand side, this is a fixed, right-hand side is free, fixed free. And you can see that, right, when the beam is moving downward, in this case, it's downward. And so the solid curve, it means we compare to the passive approach. If we do not have a piezoelectric layer, I mean, that means the constraint, you can see the constraint layer, the top layer, right, is a stiff. That's why when the beam is moving downward, and now this will be longer than the constraint layer. So therefore, look at the solid curve here. The beta A, the shear angle beta A will be created. I mean, this is beta is called shear angle. Okay, this is with solid. I mean, this means will be, so not beta A, beta P, sorry, the passive here. So beta P, right? I mean, from here, the beta P will be created. It's pretty small range. You can look at it. The beta P will be created. So in this case, we have a piezoelectric layer. So with the voltage, we can control and we can shorten it from the solid curve. You can see the location will be shortened and to the dashed line. So of course, the drawing here is kind of the exaggerated. Okay, we want to make it clear. Look, I mean the better illustration. So it'll be shortened. So if you shorten it, you can see both ends, and the shear angle beta P will be increased to beta A. So beta A is from here to here. You can see with the arrow here. The beta A will be for the whole, basically the part. So what happened about the pen is not working? Yeah, this is the angle I'm talking about. It'll be larger, I mean beta A. So you make it beta A will be greater than beta P. So that's the purpose. I mean, after the control, right? So now, if you look at the bottom, the description, the active the piezoelectric copper sheet on the passive viscoelastic layer has been, this is a configuration. And when we do the control, the active action will increase the shear angle, which is a beta. And therefore, the system damping and can be increased, can be enhanced, because the larger the shear angle when the thing is moving up and down, and more energy will be dissipated. And then the damping, with the damping effect, the vibration, the amplitude will be reduced. So that's about the idea about this approach. And let me show you another scenario. This is when the beam is moving downward. Okay, I mentioned here, just utilize here. And the next one, actually, this is a case, right? Exactly the case. So the beam is moving downward, and the lower one, I put down the beam is moving upward. Okay, so here you also can fill up this is the original, is a beta, and this is a beta P is small, and will be increased to beta A. You can just refer to the previous one for this. Beta P increased to beta A, right? So now, look at this at the bottom. When the beam is moving upward, so in this case, the passive is still the solid curve, right? So the beam moving upward, the length here, actually the corresponding length here will be like shorter as compared to the constraint, the top layer. So the top layer is a solid. So therefore, the beta P will also be formed. The smaller angle here, for this, beta P. This here is beta P. And so in this case, just use, original arrow is okay. Okay, this is a beta P. And now in this case, right, you can apply the voltage to the piezoelectric layer on the top and make it longer. You can expand, you can see that from the solid here and move it to here. And on this end will be, you can see you also can increase it. So therefore the beta and the shear angle can be increased from beta P to beta A. Let me see, I can just put it down. So the smaller angle here, and this is a beta P, okay? And the larger angle is beta A, beta A. And the idea will be, again, make beta A greater than beta P. That means with the active, right, will be better than the high, greater than the passive, the angle. So in that case, the overall, the performance when the beam is moving, downward and upward, we keep changing, the voltage applied to the top layer, the piezoelectric layer, we can control the structure. So this is a so-called active constraint layer damping treatment. And so if you are interested, you can also type the keyword and to find some references. In fact, we have done really detailed analysis about this. And so like 20 years ago, or 20 something years ago. So that's about the example for this. So beam, you have a question about the beam. So beam is like this. You have a structure, it can be very, you have many different kind of structure. So beam will be, you can see this is like so-called, we call this as 1D structure, one-dimensional structure. And because what you need to do is, you can see that is along this so-called axial direction, longitudinal direction. And maybe you can treat this as a ruler. And there's a ruler, right? If there's a ruler, let me get a ruler here. So here's a ruler. Can you see that? Or maybe it's not very clear. Let's see. Okay, hopefully you can see that. So this is a ruler, right? It's a ruler, I mean regular ruler. So this ruler actually is a beam structure. You'll be example, you can see that, right? It's long in this direction, and it's the thin. And then if this one fix, I move, you can see, you can see you'll be have a movement, right? You can move up and down, I mean, right? Okay, so this is we call this as a beam structure. And now if you extend it to the 2D, I mean, not just this is the X, you can see in also another direction, like a paper, if the paper is not that soft, okay? If it's very large, and the paper, this one, if it's thicker, you can treat this as a plate. We call it 2D structure, two-dimensional structure. Now, if you consider some other, it becomes three-dimensional. So it's related to the coordinate you use. For this kind of structure, the coordinate to use only, like for example, X, the spatial coordinates X along the beam is one spatial coordinate you need. We call it one-dimensional structure. If you need the X and Y is a plane, right? It'll be a plane like this is a two-dimensional. You need to X and Y, and then this we call it 2D, two-dimensional structure. And if you need X, Y, and Z, we call it 3D structure. So this is a question I answer, I mean, okay? So you also can check in fact, for the beam, for this very thin beam, there's a name, we call it Euler-Bernoulli beam. And because in that case, it'll be easier. If the beam is very thick, it's much thicker, then you have to consider more. So the corresponding the theory you need to basically consider will be also different. But now, as you will see, we'll consider the simplest case first, which is a cantilever, I mean the Euler-Bernoulli beam. So you'll see the basically more discussion about this part. Got it? Now, if this is fine, let's go back to, as I mentioned, right? We would like to talk about the what semi-active here. Yeah, the semi-active control. So we still have one more control. I mean, we talked about 3 already, which is a passive active and active passive hybrid. And for semi-active control, it will be, hey, if you consider the MCK, I mean the MX double dot plus CX dot plus KX equal to F. So we just try to control parameters, right? The parameter could be MCK. I mean, we are talking about here will be MCK. C. Just use C and K. So we are not going to use force directly. And one very common is to control C, the damping directly, right? To control the damping. So, and we call this as if you can control damping, is an adaptable energy dissipation device. That means the C is now controllable. It's controllable. So I can draw the diagram again. In this case, semi-active. Let me find space here. So this is a semi-active. And the first example, again, will be single degree of freedom system. Easier for you to compare. Okay, so this is a M, and this is a K and C. It looks like nothing special, right? But this C, I add an arrow here. The arrow means this C is controllable, it's not fixed. It's within certain range, you can control it. And so this one we call for example, will be controllable damper. I mean, the damper is controllable. So, controllable damper, D-A-M-P-E-R, damper. So for example, will be MR damper. MR damper will be the example, right? So with this, the damping coefficient is not fixed. It can be controllable. So this is a example. And let me show you again, back to this one. Let me show you this. Right, this will be the case, will be the example. So we have a semi-active, say the case, and now is for the suspension system, used as a suspension system. So like this is a suspension system. We have a vehicle body, and this is a spring. And now this damper, we can replace the regular traditional viscous damper. Now can become the MR damper. So the MR damper is, for example, we have a measure response with a controller with a feedback, and we can control the micro-sized particle within the MR fluid, right? So therefore, with this kind of control, and now the corresponding damping force can be changed within a certain range, and therefore the overall will be to reduce the amplitude of the vehicle body. And so we call this as a semi-active suspension system. All right, so this is a good example, I mean, to show. And in fact, for this example, it's already some commercial car, they do use a MR damper and in the suspension system. So this is an example for the semi-active suspension system. Now, as a summary for all the method here will be back to this one, semi-active, right? So the purpose is for both methods showing on this slide, either the active-passive hybrid or semi-active control. We would like to combine the advantages from both active and also the passive. So with this in general, that means the high performance can be obtained, and the system still stable is also fail safe, and also we are able to have a lower the power requirement. I mean, with this, the power requirement can be low at OW power requirement. QUIREMENT requirement. Okay, low. That means compared to what? Compared to the previous one. So requirement, this is a sparing requirement, and I compare to active, and usually the power requirement will be high, right? So now these two methods have a similar benefit or the similar objective. We try to lower down the power requirement with a little power, and then we are able to obtain high performance. So that will be overall the discussion, I mean, we have here about the structure control. So any question? So no question? Okay, if not, that's good. I mean, this is here is mainly those key concepts. So next time we'll talk about some math again. Go back to the math, for example, because structure control is a continuous structure or non-parameter system, we are able to put it down like this. It could be multiple degree of freedom like this, right? And then with this, how we are going to when the structure control, how we are going to change a model in order to incorporate into the control, because the control will be part of it, right, for easier simulation. So it's not complicated. In fact, based on this, only a few steps, we'll be able to change a form into the so-called state space form. So this is also quite close to if you study modern control, and you also have it and use it. So we can link and this part and to the modern controller, that part. And so for those controller you are familiar, you can just use it, I mean, directly, and for controlling the structure. So that'll be the purpose. So I mean, time is, I think it's up. So question about this? So we are in the right track. And so you can work on the assignment, I mean, number 2 when you have time. And also think about the course project. Okay, so this is what I want to remind you. And if you don't have question here, and then I will talk to you next Monday. Okay, and then we'll continue the discussion here about the structure control. And then after that, followed by, we'll talk about the sensor and actuator, which is will be part of the control system, the key elements within the control system. Okay, no, if no question, then we stop here. And thank you for your attention. Bye.